oh, this is one of those series, and I'm supposed to determine convergence or divergence, and so maybe you would go with this. I think this would be a really logical place to start. Limit as n goes to infinity of n over n squared plus 1. What am I attempting to do here? Nth term test. So if I do the nth term test, you could arrive at the answer a number of ways, but what do you think the answer is? It's 0. You could even use the pre-calc trick here, couldn't you? Couldn't you say, hey, they're both polynomials and the numerator's degree is 1 and the denominator's degree is 2? And in that scenario, don't you head towards 0 long term? Or you could do L'Hopital's rule, or you could divide everything through by n squared. There's like 2-3 possibilities for ways you could get there. The bottom line is, if you get that for an answer for your nth term test, what does that mean? Nothing. It means nothing. Other than it maybe doesn't diverge, or maybe it does. We don't know yet. It basically means nothing. The nth term test is silent. So maybe you erase that, or you cross it out or something, and then you go through kind of your sequence of thinking. You're like, okay, what are some other tests that I know about? Oh, the geometric series test. That's pretty cool, because if the common ratio is, the absolute value of the common ratio is less than 1, then we get it. Is this even a geometric series? How do I know?
The plus 1.
Well, the plus 1 maybe, but like.
And on the total.
Okay, yeah, but like categorically, we were talking about totally different things, right? This is variable to a number. What's a geometric series? A number to a variable, right? So whether we deal with the plus 1 or not or whatever, the bottom line is it's just totally the wrong thing as far as the geometric series go. Let's see here. If it's not a geometric series, it's a p series, right? P is 2, which is big. It's not a p series? Why is it not a p series? Yeah, certainly the n on top, that would need to just be a number, preferably a 1. But if it was another number, we could just factor it out.
No.
And how about the plus 1? The plus 1 also means it's not a p series. Remember, a p series is specifically 1 over n to the p. No plus anythings, no variables in the numerator. Yes, ma'am.
So say you had something like 1 over, and then in parentheses like n plus 3 to the squared.
Yeah.
Would that be p series because you could do like a u substitution or something?
So our part is, what if it was, you probably could navigate that. There would be a faster way we haven't looked at yet. You might be able to navigate that with substitution, I suppose. That thought hadn't occurred to me too much because there would be an easier way to deal with that.
Okay.
So a lot of this is about, and this will be certainly a work in progress, a lot of this is about being efficient, right? Because we might look at one of these and find, hey, there's like 4 ways I could do this, but that one's fastest. So let's do that one. So yeah, it's a fair question. So the other thing remaining of all the skills, things we've looked at, is integral, right? Because it's not a harmonic either. This is going to have to be, guys, an integral test. So here's what this would need to look like. I'll do this fairly briefly. Limit as n goes towards infinity. Sorry, not n. Let's go with b. Limit as b goes towards infinity. I was still stuck in nth term mode there. Of this. So to use the integral test, you simply take the nth term and you turn it into the integrand. And in order for this to work, you got to use a limit, right? Because it's an improper integral. So, limit as b goes towards infinity. What's the antiderivative of n over n squared plus 1? I don't think so. That's a pretty darn good guess, but I don't think so. It's going to be an ln. Yep, so it's ln of n squared plus 1, but it has to be times 1/2, right? We're missing the factor of 2. Yeah, that might come up later. But you know what? You bring up a good point, because sometimes the difference between an integrand being this or that is just one little tiny detail that you might not even notice. So you bring up a good point. Okay, so then limit as b heads towards infinity. It'd be 1/2 ln of b squared plus 1 minus 1/2 ln of 1 squared plus 1. So then when you look at this and start to evaluate this limit, It's ln of infinity squared plus 1. What are we talking about? What's infinity squared plus 1? It's infinity, right? We're heading towards infinity still. And what's the natural log of something heading towards infinity? Infinity. Well, what's half of that? Infinity still. Minus 1/2 ln of 2. We're going to get infinity. And so here is the big step right here. You'd be tempted right here to just stop, because doesn't it feel like we've stopped? What we'd need to do then is put therefore the series, not the integral, because the question was about the series, not the integral. Therefore, because the integral diverged, we can say that the series also diverges. And if you wanted to name it, you would call this the integral test. So you've got to finish off by actually addressing the question that was asked. They didn't ask you does some integral converge or diverge. They said does the series converge or diverge? So at this point, we've answered that question. Colin.
So over here, we were just learning or trying to figure out like how little we could write. We just write IT.
What is the minimum work?
Minimum.
And of course, you know the response to that is you're asking the wrong question. I have never seen anyone use that acronym.
Really? Information.
So I'll just leave that for what it is. I would say go back to what I said at the start. Remember that in all these types of questions, the answer is one of two things. And so really the thing is your explanation. So maybe I wouldn't try to cheap out on the explanation. A couple of them, like GST, I've seen that written a bazillion times by people other than me or you. People here at our school. Later on, AST for alternating series test. Things like that. But, go ahead, Nick.
So we don't have to specify that as a positive.
Oh, sorry. You know what? I didn't write that down. I need to. Sorry, I got distracted by notation stuff. So let's tie this up with the conditions. So we're going to say because. I'll abbreviate that for you. Is that cool? Because. BC. Because n over n squared plus 1 on the interval from 1 to infinity is what? Three things. Continuous? No. Positive, decreasing. Is continuous, positive, and decreasing. So on that interval, 1 to infinity, and you don't have to go through and prove at every single point that that's true. We just need to recognize and maybe mentally note the pattern that yes, all those terms will be positive. That graph is continuous, on that interval at least, right? I guess it's always continuous, and decreasing. Therefore, we can use the integral test. Okay. Any questions? Thank you, Nick, for asking. Anyone else? Okay. So then 3. We'll get a little repetition here. Number 3 says this. And this is likely the one that Jasmine was talking about, right? So here, again, what you would do is you would run through this. Let's just do this mentally this time instead of writing it out. In your head, you would say, hey, the nth term, as n goes towards infinity, what is that nth term going towards? 0. Not going to help us, is it? Is it a geometric series? No, it's not geometric. Is it a p-series?
Negative.
Why is it not a p-series? Because it's really close.
There's a plus 1.
The plus 1 ruins that. Okay, so is it harmonic? Because it's almost harmonic, right? What's the reason that it's not harmonic? Squared, right? N squared. If it was n to the first, now it's harmonic, and we could just say, those are always nice, right? All you have to do is say, it's a harmonic series, therefore it diverges. That's all you got to say. But it's none of those, and so in this case, we would probably use the integral test. So let's start off with the conditions this time. We can say, because 1 over n squared plus 1 is...
Positive, continuous, and decreasing.
There you go. Let's remember those. Positive, continuous, and decreasing. And let's include on the interval from 1 to infinity. I'm just matching those up with the 1 and the infinity. Because of that, I can use the integral test. So this would be integral from 1 to b, limit as b goes to infinity on the front there, of this. And thankfully, because we were kind of painted into this corner of using this, thankfully we can find the antiderivative, and it's what Jasmine said earlier, right? This is an arctan. Yay. Okay, so it'd be limit as b heads towards infinity of arctangent, and it would just be n, right? There's no adjustments or anything needed. Timmy didn't mess anything up. Evaluate it from 1 to b. And I think yesterday when we were going over this, this was probably the number one question that was asked. I got to this part, arctangent of b minus arctangent of 1. What on earth is arctangent of infinity? And what on earth is the arctangent of 1 sometimes, right? So what's the arctangent of 1? Pi over 4, yep. And what is the arctangent of b as b heads towards infinity? It's pi over 2. And this was a tough one. I'll erase this. But remember that the graph of tangent looks like this. And these are at...
That's a beautiful drawing.
Thanks, I try. Sometimes it comes off well, sometimes it's terrible. Okay, so there's tangent. And so, of course, arctangent is just the reflection across the line y equals x of that, or like the double reflection, if you will. And so it's going to have horizontal asymptotes. And it's going to do... Oh, it was going to be nice. See, there's an example where it's not very nice.
Oh, that's pretty good.
We'll do that.
Oh, that's
There we go.
amazing.
Even better. Something like that. And so then you ask yourself, all right, well, where are those horizontal asymptotes? Because that would make all the difference, right? Well, if the vertical ones were at pi over 2s, wouldn't the horizontal ones be at pi over 2s, like every pi? Just a flip. So this up here is at pi over 2. This over here is at negative pi over 2. And so as b gets bigger and bigger and bigger, heading off to the right there, that graph will be getting closer and closer to pi over 2. Okay, so like I said, I'm going to erase that with question.
Yeah, is there any way besides looking at a graph to figure out the limit?
You could look at a table,
Oh, okay. But
which
there's
is essentially a graph.
Yeah, but there's no way to like numerically find it.
You could think about the unit circle.
Yeah, I guess.
You could translate it over to the unit circle a little bit,
Mhm.
but you'd kind of have to know what the graph looked like in order to do that. So
Yeah.
maybe you just think about the graph.
Yeah, I guess the graph is the easiest.
Yeah.
I was just trying to think if I wanted to justify my answer, but graphing is too much work.
Yeah, but a table would be fantastic, right? Because you'd say, okay, let's make x go from 100 to 1,000 to 1,000,000 to 1,000,000,000 to 1,000,000,000,000. And if you had a calculator, if you had a calculator, you just graph it,
Yeah.
right? So it is kind of a catch-22.
Yeah.
Or it could be that we go over it enough times, and if it just so happens this gets asked sometime later, you're like, pi over 2.
Yeah.
If that makes
okay,
sense.
that's true. And negative infinity.
Or negative pi over 2 if you're heading to the left. Yeah. Yep. Okay, so let's make sure that we finish this off right. Question, sorry. Did I miss something?
No, it was about, it's kind of for the natural log version of this, like where there's an n on top. Since there's a simple trick for like harmonic, you said simple harmonics, where it's 1 over n plus 1.
Yep.
If there's like n squared, but then there's one degree lesser up top, is there?
We're going to start talking about that in the next couple of sections. So hold that thought. There is a pattern to be seen there. There is. Yes, sir?
Does it matter what this equals? Like, does it matter that it's pi over 4?
So, okay, yeah, let's finish it off. Let's talk about that. So this obviously equals pi over 4. And the most important thing about that is it's not infinity, right? That's the most important thing about this. So, Johnny, I think you're saying, like, do I need to be this specific or this specific? Is that kind of what you're getting at?
I mean, like, if you knew that arctan of infinity was a number,
Yeah. So somebody asked this, maybe, I don't know who it was. Somebody was asking, like, what if we just knew that arctan of b as b goes towards infinity? What if we just knew that it wasn't infinity?
That was me.
And we said, was that you? Yeah. You know, what, would I be marked off for that? Like, I don't know. Like, I wish I could just definitively say there's no way that that's going to matter, but it could matter. I can see a multiple choice. In fact, I know of a multiple choice question in which there's like these question along these lines. It might just be an improper integral, but it's about, hey, this improper integral diverges because of which of the following. And if you are not able to calculate or figure out or do a table or a graph or do something to figure out what the number is, you could be in trouble as far as understanding why. So I'd love to just give you a definitive answer of yes or no. So I'm going to go with yes, just in case it's yes. Does that make sense? Okay. All right, so then we still haven't finished this one. We need to say, therefore, the series that we were even asked about, because the improper integral converged, the series also converges because of the integral test. Okay. How are we doing? I keep trying to give you all the big picture ideas. Hopefully it's sinking in. Question, Colin, Jaden, before I erase?
What's the...
This is the graph of that as and.
Oh, that's
Positive continuous P decreasing. That would be confusing. Okay. Are you guys good now? Okay, cool. All right, so then let's look at number 5. So we're good. Okay. Guys, again, I think it's really important that we take the broad view here. It'd be easy just to be a math factory and just start spitting numbers out. But let's make sure we try to get a sense of concept. There's an interesting thought here. I don't know. It might be harder to get to this than we want. I don't know. What if you did the nth term test? Because that maybe would be the first thing. I mean, I at least mentally try to think about that each time first, right? Because if nth term is something other than 0, you're done. So it's worth considering. What do you think the nth term tells us? If I did limit as n goes towards infinity of n over square root of 1 plus n squared. Might be more trouble than it's worth. I don't know. What does your math intuition tell you? 0? A little bit less than 1? Intuition actually plays more of a factor into math than you think. It's good to try to dial in your math intuition. Heard a 0. I've heard like a little less than 1. Anybody else have a thought? Yeah, he cheated and used a graphing calculator. It requires no reasoning whatsoever.
I'm just going to say infinity just so we have it right there.
Oh, so we could just be done. All we need is something other than 0, right? Infinity being the extreme.
I'm going to go with root 3 over 2.
So I'm being realistic about this. Maybe you think about this. Maybe it's a quiz or test and you look at that for a few minutes and you think, I really don't know what this is. If that's the case, you need to move on and say, I don't know, I got to do something else. So could I use the geometric series test here? Is it a harmonic series? Is it a P series? I'd have to do integral test. If we can't get anything out of the nth term test, if we can't get anything out of those other ones, at this point we'd have to use the integral test. So let's do it. Limit as b goes towards infinity, integral from 1 to b. I really, really, really want to rewrite this. Any ideas on what I should do to rewrite this?
Use substitution.
I could do that, but even before I did that. Say again, Jack? No, John? Flip up is going to be the right move. Let's talk about why it's flip up. Why is it not natural log? Square root. Not going to be natural log because of the square root. Why is it not arc sine? Because it kind of sort of looks like arc sine.
The n in the numerator.
The n in the top, and it should be minus, not plus, right? So otherwise it sort of kind of looks like arc sine. It's obviously not arctangent either because of the square root and the n. So flip up would be the way to go. And thank God it's not some partial fraction with a square root. Because that would be unpleasant for sure. Right, okay. So then, did Timmy mess this up? Yep, he's off by a factor of 2. So we go 2 multiplied by 1/2. Does that make sense? All right. So Timmy is fixed. So this would be 1/2. Limit as b heads towards infinity. And it's going to be 1 plus n to the 1/2 divided by 1/2. That's kind of convenient. This and this cancel out, don't they? That worked out well. So then we'd have limit as b heads towards infinity. And it would be 1 plus b to the 1/2 minus 2 to the 1/2. Okay, so square root of 2, bless you, is what it is. What about 1 plus b to the 1/2 as b gets huge?
It's a big boy.
Heading towards infinity. And of course, infinity minus the square root of 2 is still just infinity. Okay. What does that mean? So the integral diverges. Therefore,
It's a series divergence.
why was I even allowed to do this?
Positive.
The conditions. There we go.
Didn't check it.
So we can say because this for 1 over root 2, 2 over root 3, yeah, is positive, continuous, and decreasing. And I don't know about the interval here. I was just trying to do some numbers in my head. I'm quite sure it's positive. I'm quite sure it's continuous. I don't know if it's decreasing on 1 to infinity. The way you could figure that out is just by plotting some points, right? So the first one would be 1 over the square root of 2. Wouldn't the next one be 2 over the square root of 5? Right? So is 2 over the square root of 5 smaller or bigger than 1 over the square root of 2? Smaller? Okay. So I think once you get past those first couple, the squaring will kind of take precedent. And so I think maybe we can say that this graph is positive, continuous, and decreasing on 1 to infinity. You could also just graph it and maybe get a sense of it.
Oh yeah, it has an asymptote.
Where?
It looks like the graph is arctan.
Okay, so that's why we're checking the conditions here. So you don't think it's what?
I don't think it's decreasing.
I don't think it's decreasing.
You don't think it's decreasing?
As a horizontal asymptote.
And as b gets bigger, it's just gonna keep getting bigger.
So you're saying there's a vertical asymptote?
Horizontal.
Horizontal asymptote where?
Yeah, one.
But that actually, so you're bringing up a really excellent point. I think, it never crosses through 1 though, does it?
I think the limit is 1, but I don't think it's.
So here's the thing though. If you looked at the graph of this, here's 1, right? And doesn't the graph, gosh, you would have to do, doesn't it do this?
No, it goes under it.
Does it ever go under it?
It's the red graph.
The red graph? Okay, so starting at 1, that's why I was asking about those early terms. I didn't know if some of those early terms maybe it increased a little bit. So maybe it does this. So here's 1. Maybe it increases a tiny bit and then does this. That's why I was asking. Does it do that or not?
No, it starts at negative, and then
It always increases?
it's the red one. Yeah, I think it would be always increasing from 0 to infinity.
I don't know about that. Let's see here. Is it always increasing?
It's an asymptote.
It's got a horizontal asymptote. No, this is worth investigating. Go to your table. You can tell. Go to your table. I don't want to erase all that work, so I'm not going to shine my table up there. You guys are looking at me confused. Go to your table, start at x equals 1, and see if the numbers really are increasing or decreasing.
They're increasing, but it's as the number gets bigger and bigger, it's going to be getting closer and closer. It's almost like technically it would be a horizontal asymptote.
Okay, and that's what I'm getting at. So was this even a decreasing graph?
No.
So it is for sure increasing up to
Yeah.
1. It's not decreasing down to 1.
Right.
Yeah.
Ah, lovely. Okay, so let's think this over. Oops. Let's think this over. I started us off by saying, what about the nth term test? What do you think the nth term test tells us? It equals,
Not 0.
what does it equal?
1.
Very likely based on the graph 1, right? So you'd go back to here and say, well, equals 1. Maybe it would have been worth our time to investigate that. Does that make sense?
Yeah.
Wow. So this is kind of maybe your first glimpse at, we spent all this time doing all this stuff right here, I guess, when we didn't need to / couldn't really be doing that anyways.
The math police will get you. That's
Math
illegal.
FBI maybe.
Yeah.
Yeah, yeah.
CIA.
Okay. Oof, even scarier.
The math Interpol.
Okay, so it's not even decreasing on the interval. So we'd have issues even using the interval test. That make sense? Cool. Do you guys have any questions there? Do you see why checking the conditions, considering all the tests at your fingertips, is always a good idea? Jasmine.
So will we just say the?
So yeah, let's. So no, let's. So the. So guys, here's what you would do. You wouldn't say, "Hey, I can't do this because the conditions for the integral test weren't met." You would stop right here and you would say, "Therefore, the original series diverges because of the nth term test." We were seeing that with the integral test as well, but the conditions weren't even technically met. Right? Like I said, I would have stopped. We could have done like a fancy L'Hopital rule version there and arrived at an okay place. So, trying.
I just took the derivative. Maybe I did the derivative wrong. But I got negative number.
Yeah, you definitely did it wrong.
That's wrong.
You did the derivative of what?
Of the function, he's trying to see what the slope would be so that, like, he'd know if it's decreasing or increasing.
Oh, gotcha.
It would
You could do a product chain or a quotient chain. I don't want to go too much further with it than that because we got other things we need to get to. I think you should, like looking at the graph, it looks like it appears it should be positive the whole time. I'd be happy to sit down and troubleshoot that with you, Johnny. I just don't want to do that right this second. Okay.
Try doing derivatives better.
Okay. Guys, other questions? We'll leave this alone for now. All right. So then we'll just get a little taste of this before we go for the weekend. We're making really good progress. This is awesome. This is actually one that we looked at before, and I wanted to make sure that we touched on this before we left. We're going to look at two different comparison tests. The first one is essentially a direct comparison, and it's just what you think. It's very straightforward in the sense of if I came into the room and I said, "Hey, I am the tallest person in this room," all it would take is for a couple of you to stand up, do a little comparison, and we realize, no, in fact, that is false, right? I could walk in the room and say, "I'm the shortest person in the room, and I'm probably taller than so." To prove that easy. Again, just by comparing, right? Does that make sense? And that's really the essence of this, just saying, if we compare the graphs of these functions, we can get a sense of what's actually going to happen. So, we did this when we did improper integrals. Like, we did a very brief version of this. Yep. So the hard part about this is the part that makes people nervous is this question: how am I supposed to pick a series to compare with? Like, who am I supposed to pick? Right? So, I looking at the coach thing again. This is a very balanced coach. This coach will tell you whether you converge or diverge. It's not going to just tell you one or the other. But what I'm reminded of here, if you've ever been a part of team sports, sometimes you do drills against a teammate. And sometimes, like if you're a really good teammate, you want to pick someone who's a little bit better than you so you'll get really pushed and maybe get a little bit better. But if you're having one of those rough days and you're just like, I don't want to look stupid, I'm going to try to pick the person I think I'm better than to play against in this drill. You know what I'm talking about? It'd be better if you pick someone more challenging. But that's, guys, that's the hard part about this test is who do I pick to compare to? That's decision point is kind of hard. So here it is. I'll draw some graphs to help us see this maybe. So direct comparison test. First of all, the condition is everything has to be non-negative, right? So the two series, A sub n and B sub n, have to both be bigger than 0. So if that is the case, and A sub n, I mean, would it be fair to say here that A is between 0 and B? That's an and. Make sense? A is between, vertically speaking, 0 and B. If that's the case, wouldn't this be the graph? Let's see, if I had y-axis, x-axis, and then here is one of the graphs. I'll just do this. And here's the other one. So if that would be the case, the blue one would be B sub n, and the purple one would be A sub n. Does that make sense? Okay, so here's the comparison test. If B converges, then A has to converge. Make sense? So if B is getting close to 0 fast enough, doesn't that guarantee that A is getting closer to 0 fast enough? Make sense? Okay, so then if that's true, maybe this will make sense. If A diverges, in other words, if A is getting towards 0 too slow, doesn't that guarantee that B is getting towards 0 too slow as well? And it's all predicated based on this condition right here. And so sometimes sketching out a graph would be useful. And like I said, sometimes it's hard to think about, man, what should I compare to? Because with these, you're only going to get one series, and you need to pick the other one to compare to. Make sense? Not always easy. Yeah.
Is this? I mean, it just reminded me of it, but is this anyhow related to the squeeze theorem? Is it just like the same concept?
Well, so the squeeze theorem allows you to find a limit that's squeezed between two functions. So you almost have like three graphs going on.
Well, could you say like the x equal or the y equals 0 is like the third graph?
Yeah, you're kind of squeezing it down. If you're looking at the first case, like if you're looking at this one right here where you're getting convergence, you could say that A is getting squeezed between 0 and a converging graph, therefore it has to converge too. I would say with the second case, maybe not as much because it's not really getting squeezed to anything. But I can see the comparison there between the two thoughts. Okay, so I mentioned here that the converse of these statements is not true. In other words, you can't flip them around. You can't say, hey, look, A converged, therefore B converges. May or may not. You don't know. And you can't say, hey, look, B diverges, therefore A diverges. You might be right or you might be wrong. We don't know. Yeah.
So would you have to keep in mind that whole hierarchy of functions thing with determining whether which one was increasing
Maybe.
more for the whole time?
Maybe. Depending on how complicated you wanted to get with your comparison. I would say most of the time there's going to be a relatively easy comparison to get to where you don't have to go there, but potentially yes, you could go there. Yeah. Okay, so like I said, the key to this is finding this comparison function, comparison series. Needs to be all positive. And here's the biggest thing, because we can all make up whatever series we want, simple or complicated. The thing is, we need to know the convergence or divergence of the thing we want to compare to. Like you might compare some function to something, but if you don't know your comparison's convergence or divergence, you're going to have issues. So we're relying on some of the stuff we've already been doing. So let's do a couple of examples here, and I think we'll call it good for the week. So here we go. Look at number 1. Use an appropriate test to determine convergence. or divergence? So guys, if you wouldn't mind, let's run through kind of the hierarchy of all the different tests we've done. So first of all, if I did the nth term test on that, what would I get? 0. So that's not going to give me anything. This is going to be potentially a little tricky. Is that geometric? It really wants to be, doesn't it?
It's just not there.
The 2, right? So close. If we could just erase the 2, we'd be good with the geometric series test. But because of the 2, it's not a geometric series, not strictly the definition of geometric series, so we can't use a lovely ratio thing, right? Okay, is it a P series? Is P 3?
No.
What would it need to be like if it was going to be a P series? End of the third and no 2, right? So it's definitely not a P series. It's not harmonic for similar reasons, right? What about, could we integrate this?
That's risky.
This would be a really unpleasant integral. We can find the antiderivative of 3 to the n, but that, no, not so pleasant. It'd be 1 over ln of 3 times 3 to the n.
Yeah.
So like pretty straightforward rule. This is not that. So we go through all the tests that we've done so far, and you'd really have to come to the conclusion, I don't have any way to do this. We got to go with comparison. So can anyone think of, and please for goodness sake, don't try to be complicated. Try to be simple. What do you think? What would be a good comparison? Okay, let's try it out. So she suggests let's compare to 1 over 3 to the n. So let's make sure we understand and see if the conditions, both formal and informal, have been met. So the formal conditions are all the terms, if we did the n equals 1 to infinity, if we matched that, are all the terms going to be positive? Yes. Okay, that's good. Where does this fit in regard to the original series? Is this, on our interval that we care about, is it going to be higher or is it going to be lower? For every single term, for this one, for every single term, the denominator will be a little too bigger, right? And if the denominator's bigger, the whole thing is smaller. Okay. So we could say this 0 is less than our original series nth term, which is less than, and I think we could probably say less than. Technically, it could be less than or equal to for a valid comparison. That's not the case here, but it could be if we needed it to be. So that's true, right? You can think about how the numbers would go. The denominator is always too bigger, so that's good. And then the last requirement is more of an informal one. Do we even have any idea about the convergence or divergence of that?
Diverges.
It diverges?
Because R is less than 1. Yes? No.
What do you think?
No, R is 1/3.
He explained himself well. Do you agree or disagree?
Dissent.
You're going to dissent. Oh, third option. Josiah, you had your hand up. What do you think? Did you say it one more time?
I did have my hand up.
Oh, I'm sorry. I thought you were waving at me. No, you were just leaning back.
No, but I'd say I would say that.
Did I say that diverge or converge?
You say diverge.
I wanted to convert.
Good job.
Josh, can I admit something? Whenever I do a series, convergence or divergence, I'll go through all the numbers and all the blah, blah, blah. When I get to therefore the series, I personally have to stop, slow down, because I find myself writing the wrong thing all the time for no particularly good reason. It just comes out. So I can identify with what you're feeling. Okay, so let's talk this through real quick. What kind of a series is this, is our comparison? It's geometric, right? Because you have a numerical base with a variable exponent. And Josh spelled it out really well. He said R, the absolute value of R, equals 1/3, and that is less than 1. Therefore, that series converges, right? I'll just put, therefore, the series converges. Okay, so here's where we get to use our reasoning. Our comparison converges. And our comparison is always bigger than the series we care about. What's our conclusion?
The series also.
Yes, our series also converges. So we can say, therefore, by comparison, that original series also converges.
So if this were to, if the geometric test were to converge, would we have had to pick a new comparison?
You mean diverged?
Diverge. Yeah.
Yeah. So yeah, if we would have set this up the way that we did right there, and we come over here and we're like, whoa, wait a minute, we got a diverging comparison.
Yeah.
If we have to go back and say, well, we got to go back to the drawing board because this comparison is not going to work.
Okay.
Yep. Good question. All right. So I hope I'm setting us up for some good practicing on Monday. It's making sense. It's like highly abstract, isn't it? This is hard to get a hold of. You'd be totally excused if you're just like, oh, this is making my head explode right now. It's okay. And of course, it'd be great if it wasn't as well, but whatever. Anything at all. I'm not going to start another one. We got like 2-3 minutes, and I want to make sure that as of today, Friday, almost 3 p.m., at least right now, you feel okay. Not, I'd love to answer a question.
So, for the quiz on Friday, is it just 9.2 and
Just 9.2 and 9.3. Yep.
So where does that stop?
Yeah, can you just go over what that covers?
So like
9.3 ends with the integral test.
oh, okay.
We just started 9.4.
Okay, perfect.
So it covers the P series too?
Yep, nth term, P series, harmonic, integral test.
Okay,
Not the comparison.
that I can handle.
Yeah, so you'll have a week to kind of continue to digest those a little bit. And the good news is like as we go through newer stuff, we'll continue to like go back and say, hey, is this a P series? Oh, okay, whatever. And so you'll get some natural refreshing of that as we go.
Get some natural logic.
Yeah, good one.